Okay. Good afternoon, everybody. So last class we went through some of the advanced application stuff you can do with Copacity. So we're reinforcing how to use this as a modeling tool. We started exploring some of the ways that you can set up a model and then start poking at it, where you're looking at time courses, and I wanted to show you sort of alternative graphing kind of parts, including the parameter scan. This is a way, again, that you can set up a model, some initial conditions, some assumptions about your rate constants, and actually create time course data where you have concentration versus time as an output from this one. So this is just, again, a way to do visual mapping of trying your own hypotheses. These should be a way for you to say, if I believe second step is rate limiting, and I think I have this convoluting feature, here's what my profile might look like as I solve the order other components. This maps over what I've asked you guys to try doing over the weekend. And again, please submit your stuff in on Monday, or sorry, by Sunday. We'll discuss on Monday that point. But one of the questions I've asked you is, given a certain set of a mechanism with certain parameters, what does the time course look like? Can you solve the order? And I'm really asking you to go and do this. Basically run synthetic experiments with different concentrations initial and see what the outcome or impact in your rate would be to come up to some conclusion. What we're going to talk today in more detail is parameter fitting. So I'm going to show you how to do that, but first I'm going to tell you a little bit about why it might matter. So this is actually some research project that came out of my group. What we were studying was the formation of this molecule over here called spiroomatad. It's a spirocyclic aromatic system. If you look at it, you've got one aromatic system here, so basically this entire part is conjugated. There's an sp3 center here, spirocyclic, so this side here is aromatic and fully conjugated. This side is aromatic conjugated. They are not cross-conjugated, so they're like an X to each other, right? So if you build this one out as a model, it's difficult to draw like this, but you've actually got this plus shape in between the two, where you have these two individual aromatic systems. From a materials perspective, this is, does anybody know what this stuff is? Just FYI. How much use it? It's used in what's called a hole transport material. It's for for solar cells, for flexible perovskite cells. Think of it as a big electron-rich conductive molecule, right? You've got all of these pi electrons. You have to functionalize it with these electron-rich amines, so you end up with something that is a big organic source of electrons to act as a conductor. That's all. What matters about this guy, though, is that the ask that came into the group was, sure, you can take this tetrabrominated starting material, this amine, and just run 4 sequential CN Buchwald cross-coupling. So this is the same kind of an idea that we've been talking about, the cross-coupling of the Suzuki reaction. Similar sort of catalytic system where palladium is going to go and do an oxidative addition. So there's that first step of catalyst plus starting material. Then you're going to do a transmetallation. You're going to add in the nitrogen. Then there's a reductive elimination, so you're installing one CN bond at a time. So you can imagine if that happens a single time, you get this guy. This one can react. If it reacts opposite, like to this one, you'll get this di-substituted product. If you go to this one, this one here, you get this di-substituted product. Or you do 3 times and you end up with a tri-substituted product. This other one here, so like across the 2 rings, this green one and the one where we're substituting these 2 adjacent, those are actually just enantiomers of each other, right? It's spirocyclically symmetric because even though geographically top and bottom, if you build it out, what you're really talking is something as a helical spin axis. So there's really this progression as you move through it. Why this mattered is the goal was to come up with a way to specifically make these kind of molecules where 2 on one side and 2 on the other side were different. So it means you got to start from that, make only this, and then react, let's say, the 2 bromides separately. So it's about actually controlling the system to get like a dye substitution strictly for what we have there labeled as the orange product. This required us to understand what the mechanism was, to understand building a ligand, to understand how we actually might approach this problem. That's why this was why we were doing it. As I mentioned, the mechanism, this is a little bit more verbose than what we've been showing, but it should show the same kind of mapping of the catalytic cycle we've discussed in class, where you can take any catalytic cycle where you're taking a free catalyst, 2 different species, and you're fusing them together. It should follow the Michaelis-Menten kind of triangle we've discussed through. I want to just highlight how that would map over. So in this case, our palladium L, that would be our free catalyst like we had in the first case. Oxidative addition, that's our A plus catalyst to make intermediate 1. intermediate 1 would undergo, in this case, we've broken it out where there's a coordination and then a base step. So this is where we have two species. Coordination, sort of like that transmetallation. Base addition is just swapping out one of these species. You're actually deprotonating that hydrogen and that X to give you this guy. So here we've added another component. The steady state mechanism from what we have here looks more complicated now. We've just added this other part. One way you could deal with the simplification to match it over the sort of normal one, I'm going to redraw this. If you had what we drew before in our catalytic cycle, a free catalyst, in this case, call that our palladium 0 with our ligand. We have our first addition to our A, that's still our aryl halide, to make what we're calling our intermediate number 1. What I'm showing you on the screen here actually has two elementary steps, the coordination of the nitrogen and the base step, where if you were trying to kind of make it a one-to-one map, what we could draw this as is my amine, my R NH2, plus my base, our starting materials of this step, and we're just going to do a warp speed move where all of these species, the amine and the base, are reacting with intermediate 1 to make, we're going to call this intermediate 2. And the output of that step would be your base HX, basically the deprotonated one. Now, the two things I want to touch on this. If you look at this, what I've drawn on the board now, intermediate 1 plus RNH2 plus base, that's fundamentally a ternary reaction, right? That is not represented what we would call a elementary step anymore. So it as no, this is an oversimplification and does not match over what would be a true elementary step. The reason we're bolting it into here is we have to assume, or usually what we might do in this case is do what we would call engineering kinetics. Now we look at this and say, I know that there's multiple transition states, but as long as one of those steps, for example, the acid-base step or the coordination step, if that is fast, this is an acceptable simplification. What I'm doing is taking the multiple steps that are possible here to make the model a little bit more tangible or map it over to something that's a bit more simplified. This is a very common thing we might do is say, I understand this is two transition states, but acid-base chemistry is fast because I've got tons of base. I'm going to lump it together. That way it's a minimal model. And then your final step here, intermediate 2, is going to do reductive elimination to make your product and regenerate your catalyst. That sort of maps over what we have here. There you can see there's one more step that we have there after deprotonation. The reductive elimination implies that we eject the catalyst or eject the product and then form our free catalyst. Yeah, sorry.
Would the product end up also functioning as a base because you would have that tertiary amine?
Yeah, you could make this more complicated to say that what we're calling base, any proton acceptor, in the practical sense, this reaction might be run with like T-butoxide, a very strong base or something. But you're right, as this reaction runs, you're actually making this material, which might be a proton acceptor. Again, for practicality, this is what we might call, it's a bit of an aside, but this is what we might call a proton inventory. This happens very common with reactions that have changes in the relative pKa of the stuff that's in the system. The reason we can sort of eliminate it practically here is, look, you start with something that is kind of basic and substrate, and we end up with something that's basic and substrate. The other assumption I'm making for that is that the relative basicity of the free amine and the arylated amine may be equivalent. And again, that may not be true. That may be a convolution. But in this sort of case, why this was at least possible with most Buchwald-Hartwigs, you're using something like LDA as your base under strong base conditions. So you're probably, if you think about it in terms of where the protons are going to go, most of it's going to be the strong base. The protonation, deprotonation of your amine is less useful, right? That's all. But everybody, okay, first part, does everybody see how a more complicated mechanism, you might do a reduction to something you've seen before? This is the art part of kinetics. You need to practice this where some of these assumptions, you go forward with them. You do this because it's a way of getting to an abridged system that matches something you've seen. This is fully appropriate. What I mean, the best practice you can do with this, though, is I will make this assumption. In doing this, especially I'm pointing to this intermediate 1 to my amine plus my base, this now ternary step. I always recognize that in addition to this simplification, I have an asterisk, an assumption I've put on top of that. Be verbal about it, document it down. In this case, I'm assuming one of those steps must be fast. I don't know which one it might be. I'm just putting a bucket around it. That assumption may be wrong. If you go through and build this mechanism and try it against your data and it does not fit this simple system, really that's a call to say we've got to expand the mechanism. This assumption is probably the first one I would focus on, and I would have to rebuild this into something more complicated. But this is an iterative process that you'll go back and forth on. I'm not saying this is true, but this is a good first step. There was one other thing under the hood here. So again, back to the class. Is anybody who has done like palladium catalyzed type chemistry like this, these kinds of cross couplings? A couple people. If you're familiar with it in some capacity though, you've seen things like CN cross coupling, Suzuki reactions, biorelation. This is a common sort of catalyzed AB kind of reaction. There is a really weird thing that palladium does, and this is actually from a historical part of the literature. If you took molecules where there was more than one halide, so in this case, imagine you have an aromatic ring where there's 2 bromides. I'm showing you what would happen if a single molecule of palladium comes through, does an insertion on one of those 2 sides, carries it through, you get to this product over here. After the reductive elimination, what's not shown here on the board, this intermediate 2 to catalyst, I'm doing a warp speed that says reductive elimination and dissociation is one step. So I'm actually saying that after the new CN bond is formed, the product disappears. Right? It just goes away, it gets away from the substrate. The thing is, if you actually go look in the mechanism, the only way that oxidative addition can happen, and this is for people that have studied sort of organometallic, palladium is kind of a very electron hungry metal, loves pi bonds. The way that oxidative addition happens is palladium will find that pi bond and actually undergo sort of an agostic interaction where it's actually attacking that pi bond first. It's that coordination of that first contact where no bonds have changed, but they're now associated with each other. That's necessary to actually undergo the carbon-bromine bond free, cleavage and the new palladium bond formation. The sigma bond metathesis that's under the hood from here to here requires a complex like this where they have to encounter each other first. And what that just means is as you're going through the reductive elimination, you can think of it strictly as, I have this compound, I'm only going to think of my new carbon-nitrogen bond formation and in ejecting my palladium. That would be like going from here right to here with a single transition state. The other way to look at it, though, is it's actually 2 discrete steps, where the barrier to that palladium dissociation is very low, but is real. There is a sort of a part to it. So it means that you could actually break down the reductive elimination into 2 steps. One where the bond formation happens, palladium is still associated with the pi system, and then it dissociates. When you look at it like that, now there's this possibility that right here, you have a competition. This complex, after making that carbon-nitrogen bond, the palladium could either say, hey, wait a minute, I've got another halogen here. I'm already associated with this aromatic ring. So installing myself into that aromatic ring is possible. I can actually go through a second cycle where this palladium is now going to do another oxidative addition, another CN bond formation, just like you have on this equivalent cycle, versus I will dissociate and get this free complex. So really, all we're trying to put an emphasis down on is there were cases where certain palladium complexes, you could start with the dibrominated aromatic starting material, and you would only ever observe difunctionalized product. So if you're watching the reaction, you saw dibrominated starting material, difunctionalized product, never observe this guy. You would never observe the monofunctionalized monobrominated material. But there are some complexes that you do see these too. So what you really have here is saying certain ligands will make this mechanism run in a sequential way where you have single carbon bond formation, carbon-nitrogen bond formation, second carbon-nitrogen. In some systems, you get this wicked fast one. And the question we had was, that would be very valuable because what it lets us do is directly functionalize 2 groups that are attached or associated by an aromatic system. If we could leverage that ring walking, I've solved my problem of selectivity because I can touch or functionalize 2 bromines that are associated by an aromatic system and maybe not touch the other ones that are cross-conjugated to each other. So we'd have to understand why ring walking happens. There was another whole part too where the community did not believe this existed. This is one of the parts before we really dove into it that was considered sort of one of those things like Nessie or something. It was an observation that people had other proposals. So at the time, the 2 competing proposals were these 2 ones here, what they would call an increase in reactivity. So if you think about it, The other way you could have that outcome, never observing that monofunctionalized material, I could start here. Let's say I get to this compound. If by adding that nitrogen, I make this center far more reactive, it could still be sequential. It's just what happens is I do the first bond formation, the palladium dissociates, but the next time that remaining carbon halogen, this center right here, what we're saying is this molecule might be so much more reactive to this carbon bromine insertion when compared to this dye-substituted starting material. You're basically saying that, yes, it's still sequential. There's no magic. There's no ring walking. But what's happening is I'm making a more reactive product than what happens next. An example of this might be if anybody's done lithal reductions of like an ester. So you guys know this is a classic point. If you reduce, take an ester and you do a reduction, the ester actually follows and becomes the aldehyde, which is way more reactive than my ester. So as long as I have sodium borohydride or lithium aluminum hydride in the system, that aldehyde is going to rip through to the primary alcohol. You never observe the aldehyde as an intermediate that has any lifetime, but there's nothing special. It's just that you're walking down in terms of reactivity from a less reactive starting material to make a more reactive intermediate that then goes on to your final stable product. There's no way to control it or pause or freeze out without having other mechanistic considerations, right? Same thing here. Maybe what you're doing is functionalizing the first time. You make a really reactive second component that just rips through and goes through, but there's no association. The other one was these ideas of what's called diffusion limiting. Maybe it takes a long time. The palladium does its job, isn't attached, but just like, I'm going to hang out near you for a while. Basically, that the rate of diffusion of that palladium away from one center is slower than grabbing the molecule and doing another insertion event, right? And that's maybe something that the ligand could have an impact on as well too. But basically we had these three competing mechanisms. The cool part about this is there's not an easy way by normal kinetics to sort of dissociate these pathways. These are all possible. If you just look at like endpoint analysis or even a computation, it's difficult to say which one of these is actually happening. So this is why we took on the problem. We looked at it and said, look, there's a possibility that the time course analysis might give us insight. If I watch how the product formation, the rate of product formation over time, if diffusion control is happening, what that means is I should be able to see formation of the dye-substituted product, which then really its formation is not directly coupled to the formation of the product. What I'm saying is if this turns into that, and there's another pathway that takes this aryl bromide and warp speeds it through to here, you have two things where these starting materials are forming that product and this product in competition. It's no longer this nice sequential sort of sequence. I don't have to go through the dye same side intermediate in order to go to my product if I have this diffusion control. Versus without diffusion control, it would look much more like A goes to B, B goes to C. So I'm basically talking about two minimal mechanisms that I can now model and say which one actually follows. The other one we did too is we went through and said, look, we're going to look at all of the normal palladium sources that might be here, and we picked, palladium acetate, which has to undergo if you start here, this is a palladium 2 source that has to undergo a reduction in order to start off. We're starting with a bidentate ligand. We're starting with the sort of Pepsi or the NHC kind of ligands and the normal sort of Buchwald ones. So we wanted to do a survey of different catalysts. This was not done by design. This was just saying these are common ones we've seen to look at sort of different points, and we're using the fingerprint to sort of categorize them. So here's the first ligand. Again, I want to just take a second. If you look at what's happening here, this is with Pepsi, the Pepsi palladium catalyst. You see the starting material aryl bromide is going down. I only ever observe this product, dye same side. I never observe two across the rings. There's only ever dye functionalization on the same side of the ring. I never observe something where one there and one there has happened. So I only have a single intermediate. So already that is interesting, right? I have a high selectivity event that's happening in the system. If you look at this though, the sequence you're seeing says the pink guy goes down, the orange one comes in. As the orange one comes in, it's being transformed over to the blue. And if you look at the relative rate there, at the highest point right here, the highest concentration, the relative rate of formation of your blue product is similar to the relative consumption of my beginning. This kind of looks like The first step, the first CN bond forming, is about as fast as the next for CN bond formings. There's nothing where it's like, remember, if we talked about that other way that this might happen, that we're somehow activating it, adding functionality to this group would seem to say that the product, the blue curve, should start going faster than the formation of, let's say, your orange one. In fact, it's the other way. The orange peak starts coming in quicker, a faster initial rate right here, compared to the blue peak on its own. The slope of that one is more shallow. So this is something where the second bond formations are starting to speak against that thing that we've activated the product. This is a nice sequential one. This actually follows the archetype A goes to B, B goes to C kind of part. If you switch over to Rufos, this looks a little different. So now what happens is, okay, still pink goes down, orange comes up, you're still seeing only the di-same side intermediate, and then product. It's just that now what happens is product is starting to come in almost at the same rate as the intermediate is coming in. That sort of starts to look like the relative concentration of my intermediate is much lower than the Pepsi. That might be a case where making my orange intermediate forms a more reactive material that then likes to go on to products. So it's like a warp move, right? You're not building up this high concentration of my yellow intermediate before my blue one starts in. What I'm also getting here is this competitive, or at least same rate of formation of my final product here in blue as my rate of formation of my orange one. What I'm talking about there is it's kind of locally looking here and saying the relative rate in this time part is similar, just because if I drew a straight line between the two, the tangent dx dt of those two lines is similar to each other. So there's a marked difference. If we go to the last one though, this is what the tri-T-butylphosphine did. This should make people worried. So if you watch what's happening here, pink goes down. We're still making only one intermediate, so we're only still doing di-same side. That's still weird. But if you look at your blue curve, product is coming in faster than intermediate's being generated, but you're still generating intermediate. This is weird because that really breaks the tie of saying A goes to yellow, yellow goes to blue. There must be another path where pink can go directly to blue and not stop at yellow at all. Like there's something very weird there where you can't say that there's a single pathway that would give you this kind of curve. There's something else going on where diffusion control might be something that you'd have to bring in this case, because that region right here, where the early rate of formation, you've got product before you've really built up that intermediate. So it's not this enforced pathway where A has to go to the di-same side intermediate, and only when you have the di-same intermediate can you make product. There needs to be another pathway you can invoke that gets you around the formation of that intermediate. I'm going to pause there. Does that fit? Yeah. You could. If you did, you should never see this.
But you could see like hardly any of the yellow intermediate. But like if it's so fast, it almost like right away goes to the blue. And
yep.
That's like when you're sampling, that's what you observe.
So again, it would never build up. And this is the thing. No, again, you're right. Okay. I want you to go through, and this is where now with Copasi, you can turn the dials to see if you can make that happen. The part that I like, the thing that makes this difficult, especially in a catalytic system, is you got to remember that a turnover can only happen when the catalyst is present. The catalyst, free catalyst here, is forming this intermediate, right? In one cycle, if some of the catalyst is bucketed in here, the kind of architecture you're trying to do is saying, oh, I make yellow, and as soon as it's made, it so fast goes on to product, it should never build up at all. Like if you try to invoke that one where you're saying, oh, pink goes down, makes yellow. As soon as yellow is made, it goes on to product. That's possible, but it should never accumulate, especially should never accumulate over 400 minutes. That's the part that's hard to differentiate. So if it was not there at all, absolutely, I'm in your camp. This is weird. So, but again, you can build this in Copasi, play with the numbers. I'm actually going to give you guys the data sets to do the fitting that we did. Yes? Yes, that would be a good way to go through this is, temperature. If this was true, the nature of the solvent is going to massively impact this one too. So yeah, you're thinking in terms of, this is why I love this as a tool. It lets you look at a time course, you can come up with a hypothesis, and only then you're using these data to say, now this is the experiment I need to go run to go and verify that, right? at a whole, all of time course kinetics is only really a divining rod to tell you which experiment you should go and run next in order to validate or invalidate a hypothesis. But yes, in this case, it's actually been shown that if you go to like very viscous naphthalene type solvents, you can push this much higher. So yes, there is a sort of peripheral point that cases that seem to have this diffusion control part will actually respond to cases where diffusion is where you're manipulating. It's a bit convoluted because remember, changing viscosity is one part, but anytime you change viscosity, you're changing dielectric constants, you're changing relative coordinating ability, which also changes the stability of these intermediates too. So it's not as easy, it's not a simple dial that I can play with that doesn't also potentially impact all the others. Again, want to pause on this. This is one of those things that going through this study and seeing these kind of differentials, like the kind of interpretations I'm presenting, this is worth spending the time and really helping it kind of get into your bones a bit. This is an advanced example, but if you can kind of sit with this, and especially more importantly, challenge what I'm telling you, go build the models and play with it. That is what I will give you guys to do, is I'll give you guys the Excel files that go in behind this. It will help you sort of interrogate the conclusions we made. But this is the fitting part. What we said is, if I have experimental data from these different systems, Pepsi, Rufos, and the tritubutylphosphine, I can build a minimal model that says I'm enforcing in Copasi a sequential pathway and asking it to say, look, your job, Copasi, is fit the data I have. Tell me if the model that I've proposed can explain the data I have, yes or no. And what we found effectively was the Pepsi data would fit this minimal model straight here, where basically starting material makes an intermediate, the intermediate makes the first substitution product, that then goes through a second intermediate and then a second substitution product. So it's a more even simplified version than this catalytic cycle. We're giving this kind of a certain sequential one. I can give you some logic why we chose this one. But what we have is saying, if I just take a linear pathway where pink goes to an intermediate, goes to yellow, and yellow goes to an intermediate, goes to a product, that explains the Pepsi data and the Rufos data, where what I have there is the experimental data are these dark blots, and these hollow data is the Copasi fit one. Basically, that's where I've fed the dark circles into the model I've built into Copasi, and I've asked it to fit that experimental data. And what it says is, yep, I can manipulate my rate constants, these Ks up here, to give me a time course that matches what you've seen. So that's a good validation that, you know what, the model I have at the top is a true sequence of pathways that's possible that explains your experimental data. Without this here, without this diffusion, this is what I would get. There was no amount of optimization for the tritubutylphosphine that you could ever get something where the product actually is underestimated compared to the yellow intermediate is under concentration of this one. It always has to go yellow then blue in terms of a time sequence. And again, all I'm saying is that this model here, what I'm showing you in this one there's not K values like the point you were saying. Maybe this K is so large that it goes on. Well, then the problem is we can't build it up. So that's where if we add this, we say that there is both this linear pathway and then what we call like a shortcut, basically. That goes right through to product. Now you could actually get a fit. Now, one thing to sit with too, if you look at the top, this sequence, this mechanism, doesn't match what a normal, like it's not detailed enough. If you look at the top, those kind of the math representation, the first thing that gets really difficult about this is full-on engineering kinetics. There are no bonds, no chem draws, there are no transition states that sort of map against this because we're doing aryl bromide plus free catalyst makes an intermediate. That intermediate spits out a product and free catalyst. Then I have another insertion event and then another product formation. If you look at this, remember what we talked about for what this reaction is? There's a substrate. There's actually a couple substrates I'm not even talking about. What's missing?
You're missing your base.
I don't even have base in my model. Yep.
And you're missing the nitrogen.
Yeah. What I did here, how we did this, and this is again as a rule of thumb practice, when you're doing these first early explorations, the simplest model is what you should put forward, even if it maybe doesn't make ChemDraw sense. The reason why is because, think of it this way. What I'm doing when I do this iteration is I'm taking some system, I'm solving for X, I'm solving for Y, I'm solving for Z, I'm solving for A. I am asking 1, 2, 3, 4 unknowns to be solved against the data I have. And if you look at here, I'm only really mapping the concentration of 3 individual things. I'm matching the concentration of my starting material, my intermediate, and my product. So I have 3 knowns and 4 unknowns, really, is what I've got. This is a linear system of equations where I'm measuring 3 components as they evolve through time, but I'm asking the system to solve for 4 individual k values. So this is what you can get into a problem called overfitting. If I actually took every one of those steps and drew the kinetically true intermediates of forward rate constant, backward rate constant, I would have hundreds of k values I could use. When you do that, if you build a model that has so many different k's that you are trying to fit, you will find an answer. It's just not going to be sensible because really, again, I've measured 3 parameters with time. But if I built the entire rate, like the actual full system, I would have to be fitting k's for 20, 100 individual values. That's like taking, has anybody ever seen this where you take any number of data and you plot it and say, I want a 7th order polynomial to kind of, to fit this data. Anything will fit a 7th order polynomial because you've got so much flexibility that your system, your function can be any convolution of data that you want. You've just got too many variables, so it's not ideal. The way that you get around this is you need more data, right? The more data you have and the more independent and if the more runs you have, you can actually build up these complicated ones. But in a simple system where you have, let's say, 4 or 5 individual runs and you're only measuring the concentrations of 3 or 4 things, you have to be really careful about not setting yourself up for overfitting. Does anybody know, like, do you have sort of a grounding understanding of what overfitting is? Everybody? Who doesn't? Okay, what I mean would be this. If I have a plane, and I'm saying I've got a data point, and a data point. If I assume that I'm going to fit this with a line, I'm saying the only thing you're allowed to change is slope and intercept, 2 variables. That, I can do a pretty good job on this. Okay, now I want to fit it to a different equation that has like maybe x squared or something else into it. Now you're going to get some curvature that's possible, but it'll do the best. If you start adding parameters like something like usually when you're doing fittings like this, it's y equals a to the x, a plus b to the x plus c to the x squared plus d to the x cubed plus e to the x, on and on and on, right? Where every one of these values, a, b, c, d, are things that the model will try and go and find a value for to make the data match. And what you're saying is x is a value on my graph somewhere here, y is the responding value. What you do is you start adding more and more parameters, you'll start to see it's going to come up with functions that do this effectively. The more variables you give, the more flexibility you give to this line, it'll find something that fits. Does it mean anything? No. It's just overfit. What you're doing is you're saying, I've created a function that will absolutely perfectly go through each of my experimental values, but if you don't have enough data points or you've added too many variables to turn, it's a meaningless fit. Welcome to Machine Learning 101. Right? This is the same thing. This is what's at the core of basic deep learning technology. If you take an ML model that you're saying, I have measured the temperature today and tomorrow, and I'm going to fit it to this massive thing of what variables are going to predict for happens tomorrow, it's irrelevant. Unless you have enough data built into your system, how many data points you have, and rigidity of what you're allowed to tune, the function doesn't matter. But really, this is at the core of basic data science 101 and ML. Has anybody ever done stuff like PyTorch and stuff too, a little bit? This is where it crosses over. I like to say that, yeah, anybody who's ever done Beer's Law, you guys are already machine learning scientists. That's all. Anything else we do in higher order is just bigger functions do the same kind of fittings. But that's overfitting. Same thing here. Too many variables to turn is going to give you a time course that's doesn't really matter. It'll fit the variables. It'll do what you asked. It just has no practical reality. Okay, let me show you how you do this. All right, back to our Palladium tutorial. And again, I will upload these parts. You'll have the video to review and how this is sort of done, but practically this is how you would do it. I have a model. In this case, I am showing you an example based on the simple Suzuki reaction I've shown you before, right? Not the one that we're showing you here with this multi-step component. That's something we're going to actually give you guys to play with. But this is my simple system of cat goes to A, intermediate to B. That's the one we've been discussing. There's my normal species. In my output parameters, I have only my concentration versus time plot. And remember, time course, if I run this, I get this one here. It's using the exact same setup as we did before with the initial concentrations and our K values that we had before, okay? So the only difference between, let's say this is a Suzuki reaction with these initial concentrations, the K values may not be right. I just picked these out of my butt, right? That's how this thing looks. If I want to fit experimental data, what I would do first is set up my prospective reaction. I've gone through and said, I've measured a reaction, this is a Suzuki reaction. I think that Suzuki reaction is obeying these individual rates, constants. It's actually this kind of series of equations. I don't know what the values of K I should put in to match my experimental data. That's the part I don't know right now. So I'm testing this mechanism with experimental data. You go down to parameter estimation here. You go over to experimental data. You want to make sure that this update model is checked. And we go experimental data, and it brings up this window. What this will let me do is I can bring in a file that has my actual concentration versus time data. Before I do that, there's a bit of hygiene you have to do before you can do this step. You will probably run a reaction. So here I have a time column, concentration of A, concentration B, and concentration product. If I just quickly plot that. So let's say this was a real reaction that you ran, and that's what it looked like, right? So it has the same basic shape that we've seen. You know, it's got an exponential type decay, it's got an order in something. The main difference is how fast they're running, and the absolute shape may not match what I've just built into my system, but they're kind of similar. The difference is the absolute time we have here has no bearing on what I just built in my toy model I have. Asterisks, these data here were actually created from Copasi. What I did is built a model in Copasi, created my concentration versus time data, pulled it back out, and now I'm going to feed it back to a new model and say, hey, can you fit this, right? So it's the other half of what we've already done now. So just in that case too, if you guys want to practice this, you can use Copasi to create data that you then go back through in that. So as a, well, the joke, fun weekend thing, you can actually use this as a mode of encoding. So people can use this where the K values are a cipher to a secret conversation where you create a model and you know what those K values are, and then you pass it to them. They have to fit those models, and then you guys can figure out where to go meet. And if anybody does that, I would be so proud. My point is, anyway, what I'm saying is that this came from Copasi. That's why it looks so perfect too, right? Once you're here though, problem is, Copasi cannot eat Excel data. Copasi brings in CSV, comma separated variables. Does everybody know how to take a or make a CSV from an Excel file? Yes? Okay, so you need to make this as a tabbed, or sorry, not CSV. I think I just misspoke. Save as, no, not template, excuse me. File, save as a tab delimited text, this one here. It's a tab delimited text data, and that's the one that we've saved this as. The only other point too, so I've already got it in there, when you do this, the syntax matters. You have to have a single column up here at the top talking about what the parameters are. You can name them whatever you want, but that's a text field. Then what you have is a grid, like a matrix, where the time and each of the concentrations needs a value. In other words, if I do this, I just broke my Copasi will not know what the heck you mean when you do this. If you're missing a data point on one line, the best practice thing to do would be get rid of that and get rid of that point. A blank data where there's not a match on a properly shaped matrix will break Copasi. That's the only part that I would mention in. So if for some reason you don't have that data point, just eliminate that line completely from your model that you're putting in. Okay, once you have your tab delimited data, you come back here. This is my experiment. I'm going to bring in my tab delimited text. And what happens when you do that? It says, okay, you're calling an experiment. I'm giving it number 1. I'll show you guys these later. This is if you have multiple data sets, you can actually set up how your parameter mapping goes and actually just quickly bring in many different text values. The thing I gave it was not a steady state diagram, it was a time course. So you have to click that radio button over. I'm going to be using a mean squared fitting. All I'm saying is I want you to do your best, and I want you to weight your errors between what you predict and what you have based on the mean squared. And now what you see here is based on the experimental data. The first column was called time, then I have A, B, and product. That came from the text file I gave it. What I have to do here under type, instead of say ignored, it is a dependent variable, so A is dependent on time, and then I have to tell it what is this thing back to the model I'm testing. A in my Excel sheet was the first reagent, so it is a species, it is a transient concentration, and that is of the thing in this model here that I also called A. That is just a quick comment. Calling it A in my Excel file, that's something I chose to do. Calling it A here, that's what you called it here. These are not immediately the same thing. This is where hygiene is really good. If when you do the experiment and you call it aryl halide, then in your model, it's a good idea to call it aryl halide so this mapping goes. This is also, again, for syntax. If somebody records the data and calls it aryl halide, you build the model and call it species 1. Okay, you need another Rosetta Stone for everybody's talking the same language. But what we have to do is go through each of these parameters and map them out. B is a dependent concentration. It is a transient concentration of the second component. And this is a dependent concentration of a species, of a transient concentration of our product. So now once I've done that, it'll auto-assign, and I don't honestly know why it does this, but it basically puts what it calls a weight value. The weight value is how much do you believe that the data you've given me is correct. This allows you to say, let's say you have a concentration value of A where you've got a really good calibration curve. You're sure that the concentration of A that you've put in is accurate. I'll give it a weight of 1, let's say. Maybe B has a really terrible extinction coefficient, has a really terrible value, has a lot of noise associated with it. You can keep it in the model, but you could say, all right, B is there, but B is going to get a weight of 0.001. What you're saying is, I want you to penalize not fitting A very high, and if you can't fit B, that's okay. I don't believe my concentration either. So basically, you give it more flexibility to sort of deal with the fact that one of your concentrations may not be right. For now, since this is totally synthetic data, I'm going to give everything equal weight, 1, 1, 1. But that's what the weight does. It allows you to sort of prioritize which concentration you want to nail down based on how your experimental thing kind of went. Once that's in place, now you've done the mapping. That's how you bring in data and you tell it what values in your real data mean something in your model. The last thing you have to do is tell it what it's going to work on. So this is where you click on this value here, the object. You use a little Kopassi swoosh symbol, and you say, I want you to go through and I want you to optimize the reaction parameters. I'm giving it access to all the Ks for each of the steps. There's 4 different Ks that this could be. I say OK, and what it'll do is bring in and say, all right, you're telling me that I can vary K1, that first equilibrium constant, between 1 times 10 to the minus 6 times 10 to the something 1 times 10 to the plus 6. You've given it a range. And it's the starting value is whatever your model actually started with. Yeah?
Sorry, what button did you press to get to that window?
So that's this first thing, object, Kopassi swoosh button brings up this window, and you say reactant, and you just click on reactant parameters and say OK. That will then populate all of these. Oh, which one? Sorry.
I'm still on the window with the concentration.
Experiment data?
Okay.
That's
Oh,
where
I
you
see. Okay.
you populate this part through, click OK. Now you're back to your parameter estimation window,
Okay.
and then you're into this one. The one thing I want to mention is if you knew something like an equilibrium constant, if you knew something like that some values were in certain ranges, you can go down and individually say, let's say first value here, you can bound this and say the lower bound is bigger or smaller, and the upper bound is bigger or smaller. You can basically expand and contract the range of K values that your model will go and look at. The defaults here, this kind of plus the 6, minus 6, that follows what we kind of, almost diffusion limited all the way to pretty freaking fast reactions, so it's not too bad. Once that's all finished, last thing you have to do is everything is set up, it's ready to run. I'm going to save it. I usually will go down here to Output Assistant. What this is doing is I pick this first one. I want to new plot that is my parameter estimation result. It's just a very fast macro that says I want to create, and you see it creates a new plot where it's going to show you the experimental values from whatever you told it and the predicted values on one plot. So it's a valuable way to say how good is the model doing. All right, so now I've got my parameter estimation. I've set this up of what it's allowed to work on. I've told it the experimental data it's going to work on. I've done my mapping against each piece of it. Down here, has anybody done Gaussian or DFT type calculations everywhere? This is kind of the same thing of how hard do you want me to try? How many computations or optimization steps do you want me to try? Right now it's saying it's doing this by evolutionary programming. If anybody, we can get into that later. These are all the different optimization tools you could use. Is anybody familiar with generally what evolutionary programming is as an optimization tool? Okay, and we will dive into that part. What it does effectively is it will make, up here, it will make a random guess of values for your k. It's going to make 20 different couples. That's what this one is, my population size. It will take my first 4 values of k, 4 random values, and it will do that 20 times. And then it runs each of those ones on my time course, and it scores each of them and says which ones are working. Whatever 4 values of k are the best, it will grab those and then make 20 new values that are similar or nearby those, the ones that worked best last time. So think of it like an evolution. Random numbers takes the best 4 numbers, takes those 4 numbers, and it will make new numbers that are associated with the best hit, the ones with the lowest score from the one before. And it just goes through that. Number of generations is 200. So it'll try 200 times. If you have more numbers, bigger population can help you find values. So each generation is going to have, instead of 20, we could have 40 different combinations. Number of generations, how many times do you want me to go through this evolutionary cycle to find my endpoint? If you're not converging, then adding more cycles or more computations is a good way to basically find your minimum at that point. That's roughly what these two things do. For a model as simple as this, if I go run, boom, I'm done. That's it. There was 600 calculations or whatever. And what you can see now is the dots, the hashes, those are my experimental values. That's what's shown here. So experimental value of A, experimental value of B. The fit value is my line. So if you look at this, what does this tell you? My model threaded the needle through all my experimental values. This model was able to perfectly fit this data. This is a pretty good fit that says that is my value. Now, if you go back, look at what happened to the values here. When I click Update Model, it went through that cycle. It computed the lowest score. It returned the values. And what you see is it's updated these to, that's a tiny value. This is 0.6. That's now 53. And that's a tiny value. Those are the real Ks that fit your volume to get your experimental data. Now back to what we talked about second first class. If that was my system, this guy here, where's my rate limiting step based on what you see on those numbers there? Which is my super slow step? Yeah. 4. This seems to fit a model that's my slow step. Cool. My super fast step, transmetallation, right? Equilibrium constant, the ratio of these two, I can pull that out of here too. Now here, let me show you something. This is the overfitting problem. There are 4 values. You saw the data. It's a great match. Are you willing to write to the CSC and say, guys, these are the K values I would like to enter for this experiment because they're authentic and they're new. It's like a temperature, this is a melting point. This is a colligative property. I have 4 things I'm fitting. I only have 3 pieces of data. If I push run again, what just happened to the numbers? Look at the fit. Wait, let me close this. I will bring up the fit. The fit is still fine. The numbers are not the same. Which is the slow step now, though? Slow step? Yeah? Okay, let's do it one more time. Run. New numbers. Same good fit. This is why replicates matter, because we're overfitting in the end. in the end, all we have is I have a series of values where one run to extract rate constants only from this one is a terrible idea because I only have 3 experimental values and fitting 4 things. If you did multiple experiments with different initial concentrations, this will lock in as only one real true because it has to fit those constants across many different initial concentrations. That's how we would get to authentic. Yeah?
Do you know if they use the least squares solution? Because the least squares solution will look for an overdetermined and underdetermined.
Again, that's the other part of this too. Depending on which kind of optimizer you use and how you're scoring your error, you can do better with less data. The better one though, just the thing I'm trying to emphasize for right now is do not run to, this is one data that's overfit, but that's the visualization of what overfitting looks like. I want you guys to play and practice this. I'm going to post these files back up. I want you to practice doing this kind of parameter fitting. I want you to try and do this parameter estimation. We're not going to be doing a lot more of this specific one. We're going to transition back towards the end of next week into other classical points, but this is an undercurrent, and coming back to this is a tool that we will use liberally throughout the course. And again, I'm expecting you guys to practice and play with this. Thanks, guys.